Welcome to Brain Vision.
So let's see here. In this problem, we have another Rankine cycle, and we want to basically compare a Rankine cycle, an ideal Rankine cycle, and a Carnot cycle. So in the TS space, we have these two kind of cycles. So we go from in a Carnot cycle, we just go from saturated. We go from saturated liquid to saturated vapor in the boiler. Here, in this case, in the Rankine cycle, we go from saturated vapor, or in the ideal Rankine cycle, because we go from saturated vapor at the exit of the boiler to saturated liquid at the end of the condenser. So basically, just a little different cycles, and this is more efficient. But this one is more basically practical to use. And neither of these, because both of these are ideal. So the pump and the turbine are not going to be isentropic. So these are not going to be vertical lines, regardless of what you do. So in both cases, again, we have a saturated vapor at 0.3. We're going to assume that P2 and P3 are both 5 megapascals in both cases, and P4 and P1 are both 50 kilopascals in both cases. Again, we have a saturated, for the Rankine cycle, we have a saturated liquid at 0.1, and in the Carnot cycle, it's a saturated liquid at 0.2. So we have, looking at the Rankine cycle first, we can get the enthalpy, the specific volume at 1, which allows us to get the work that was put into the compressor. That allows us to get the enthalpy at 0.2 from the conservation of energy about the compressor. So then we can get everything we need at 0.3 because we know it's we know the pressure and we know it's a saturated vapor, so we can get this information. Knowing that we have an isentropic turbine, S at 4 equals S at 3. We know the pressure then, and so now we can get the quality factor and the enthalpy at 4. And now that we know the enthalpy at all of these positions, we can get the heat transfer in is 2,449 kilojoules per kilogram. The heat transfer out is 1,730.7 kilojoules per kilogram, which means that the net work that we get out of this Rankine cycle is 717.9 kilojoules per kilogram. The thermodynamic efficiency, which is this divided by this, is then simply 29.3%. Now, in the Carnot cycle, we have, let's see here. In the Carnot cycle, we have H3 is the same as before, and T, but now we find T3, which is then also T2. Okay, so we know H3 and we know P3, so we get T3, and in a Carnot cycle, T3 and T2 are the same. So now that we know T2, we also know P2, so we can get H2 and S2. Then we know that S1 is S2, so we can go back to there and we can get the quality factor there is 28.14%. And then we can get the enthalpy at H1. Now that we know, we know the, what do we know here? Oh, we know also the enthalpy at 0.4 is the same in both cases. Okay, because we were at a saturated vapor here and same pressure, and then we went down to here. So the enthalpy at 4 in the Carnot cycle is also this value here. So we can figure out that the heat transfer out is the enthalpy here minus the enthalpy here. So this minus this. No. What did I say? 3 minus 2. Oh no, that's that's in. Yeah, that's here. That's this guy. This minus this. The enthalpy here minus here. Out is the enthalpy here minus here. So we have this value and we have this value. And then the net work is the difference between this and this. So that's 557.5 kilojoules per kilogram. And then the thermal efficiency is this divided by this. And for the Carnot cycle, we see that we get a thermal efficiency of 34.0%. So again, Carnot cycle is kind of the ideal cycle. You can call this an ideal Rankine cycle because for a Rankine cycle, it's ideal because of the isentropic behavior here. And for but we can see that the ideal Carnot cycle is more efficient than the ideal Rankine cycle. And that would generally be the case, not just for this particular set of parameters.